Welcome back to Basic Electronics. In this class, we will look at op-amp filters. For some simple circuit, we will work out the transfer function and figure out the type of the filter. For more complex circuits, we will describe the functionality with the help of plots obtained with circuit simulation. Okay, let us get started. In practice, it is not possible to realize the transfer functions that we have been discussing, and therefore the ideal filter response is approximated with a suitable h of j omega, which can then be obtained with circuit elements. For example, h of s could be 1 over this fifth order polynomial in S, and this could be a fifth order low pass filter, provided of course we choose these coefficients appropriately. Not any fifth order function will do, we have to choose the function appropriately. Some commonly used approximations or polynomials are the Butterworth, Chebyshev and Bessel and elliptic functions. We will look at some of these. Coefficients for these filters are listed in filter handbooks. So filters are fairly well studied, several decades earlier in fact, and a lot of information is available already in the literature. There are handbooks which give all those coefficients that we require. There are also programs for filter design available on the internet. Let us get familiar with some definitions now. Here is the ideal low pass filter response, and here is what we would get in practice. Here is the ideal high pass filter response, and here is what we would get in practice. A practical filter may exhibit a ripple like this one. Here we have a flat response, but here the transfer function magnitude is varying with frequency. That is called a ripple. A max is called the maximum passband ripple, this range here, and of course it is small, something like 1 dB typically. For some filters it is just 0 dB, so we actually have a flat magnitude of h in this region. A min is the minimum attenuation to be provided by the filter, this quantity here, and ideally of course we would like that to be infinity. In practice we might get something like 60 dB. That depends of course on the order of the filter. Omega s is called the edge of the stop band, this one here and this one here. Omega s by omega c for a low pass filter, the ratio of these two, is called the selectivity factor, and that is a measure of the sharpness of the filter. If omega s and omega c are very close, that means our response is going to be much better. We're going to have a very sharp drop here in mod of h, and that of course is preferred. This range from omega c to omega s is called the transition band, this one here. And of course whatever we said about the low pass filter has counterparts also in the high pass filter case. Alright, so what we are going to do now is to look at some specific filter types and their transfer functions, and then we should be able to relate their transfer function to these definitions that we have looked at. Let us look at some practical filters. For a low pass filter, h of s is 1 over this polynomial in S, which is normally written in terms of S over omega C being the cutoff frequency. And these coefficients AI for various types of filters are tabulated in handbooks. We don't need to reinvent the wheel. Let us now look at mod of H for two commonly used filters, namely Butterworth filters and Chebyshev filters. For Butterworth filter of order n, this is mod of H as a function of omega, and for Chebyshev filter of order n, this is mod of H as a function of omega. Here this Cn is actually a function given here. Now this is the low pass filter. We can make up the H of S for a high pass filter simply by using this transformation. So S over omega C should be replaced by omega C by S in this expression, and we get a high pass filter with the same cutoff frequency. Now these actual polynomials we are not discussing here because they can be found in handbooks. Here are some examples of Butterworth filters and Chebyshev filters. In the plots on the left, these two, we plot mod H on a linear scale versus omega also on a linear scale, and this omega is normalized with respect to the cutoff frequency omega C. What is the major difference between these two plots? We see that there is a ripple here in the Chebyshev filters, whereas in Butterworth filters there is no ripple here in the passband. Alright. Now in practice, the plots on the right are more useful, where we plot mod H in dB versus omega on a logarithmic scale. Why are they more useful? Because from these slopes we can immediately tell what the order of that filter would be. If the slope is minus 20 dB per decade, then we know that the order is 1. If it is minus 40 dB per decade, the order is 2, and so on. And higher the order, better it is, of course, because that brings us closer to our ideal filter. Ideally, we would like that to go to infinity at this point, go to minus infinity at that point. But of course, if we use a higher order filter, it requires more components for implementation. So there is some trade-off. Here are the corresponding plots for Butterworth filters and Chebyshev filters for high pass filters. And they are very similar to the low pass case, except of course that the functionality is now different. The high frequencies are passed and low frequencies are rejected. Once again, in this plot where mod H is in dB and omega is on log scale, we can make out the order of the filter from the slope here. So this slope would be 20 dB per decade, that would be 40 dB per decade, 60 dB per decade, and so on. Let us now look at how a filter can be implemented in practice. We will first look at passive filters, which use resistors, capacitors, inductors, no transistors or op amps, and then we will look at op amp filters later and see what the advantages of using op amps are. Alright, here is an example, and the transfer function is 1 over SC, which is the impedance of the capacitor, divided by R plus 1 over SC, and that can be rewritten as 1 over 1 plus S by omega 0. Omega 0 is 1 over RC, and the corresponding F0, the cutoff frequency in Hertz, is omega 0 by 2 pi, and with these component values it turns out to be about 318 Hertz. So this is a low pass filter, and in fact we have looked at it earlier. Here is the magnitude plot, mod H in dB versus F in Hertz on a log scale. So the gain is 0 dB here. The transfer function magnitude is 0 dB here, because for small values of omega this term is small and h of s tends to 1. This is the high frequency part, and as we would expect, mod of h keeps going down as the frequency increases. And if we relate this to the Bode approximations that we have looked at earlier, the intersection of these asymptotes, this asymptote here, the low frequency asymptote, and the high frequency asymptote, would actually give us the cutoff frequency. So the cutoff frequency would be somewhere here, and that is 318 Hertz. The SQL file for this example is available and you can take a look at it. What is the order of this filter? Let us look at this slope here. If we go from 10 raised to 4 to 10 raised to 5, we go from there to there, and that is 20 dB. So the slope here is minus 20 dB per decade, and therefore the order of this filter is 1. And that is also apparent because we have a first order polynomial in S here. So that is something that we would have expected. Here is another passive filter example, and it uses an inductor now. The transfer function is derived here. Essentially VO is obtained by voltage division. These two are in parallel. So SL is the impedance of the inductor, 1 over SC is the impedance of the capacitor, those two in parallel, divided by R plus that parallel combination. And when we simplify things, we get this expression here. This turns out to be a band pass filter with omega naught equal to 1 over square root LC, or F0 equal to about 8 kilohertz in this case with these component values. So it will pass frequencies in this band here and reject frequencies which are too low or too high. Let us now discuss op-amp filters, also called active filters, as opposed to passive filters which use resistors, capacitors, inductors. Op-amp filters have certain advantages. They can be designed without using inductors, so that is a significant advantage because inductors are bulky and expensive. Inductors also exhibit non-linear behavior which arises from the core that they use, and that is undesirable in a filter circuit. With op-amps, a filter circuit can be designed with a passband gain as opposed to a passive filter. If you recall, we have seen this RC low pass filter in which the passband gain was 1. With an op-amp filter, we can have a passband gain more than 1, and we will look at some examples. Op-amp filters can be easily incorporated within an integrated circuit. That's another advantage. However, there are situations in which passive filters are still used. Here are two situations. High frequencies at which op-amps do not have sufficient gain. That is one situation in which we would like to use passive filters. Second situation, high power which op-amps cannot handle. So that's another case. So with this background, now let us look at some op-amp filter circuits, how they operate and how they do the filtering action. Here is a simple filter circuit using an op-amp. How do we go about analyzing it? Op-amp filters are designed for op-amp operation in the linear region, and we know a lot about the linear region already. Namely, V plus and V minus are approximately equal, and these op-amp input currents are 0. And in fact, this circuit is very much like our inverting amplifier, except our R2 is now replaced with this impedance, which is R2 in parallel with C. So the gain then would be VO by Vs remember VO and VS are phasors now, is minus Z2 by Z1. Z2 is R2 parallel 1 over SC, the impedance of the capacitor, divided by Z1, which is R1. And if we simplify this, we get H of S equal to minus R2 by R1 times 1 over 1 plus S R2C. Now this part provides the passband gain, and this is the filtering action. And in fact, we have looked at the plot of this second expression, the magnitude as well as phase. So this is a low pass filter with omega naught equal to 1 over R2C. That is, F naught in this particular case is omega 0 by 2 pi, which is 1.6 kilohertz. So this circuit will function as a low pass filter with a cutoff frequency of 1.6 kilohertz. And that is the plot of mod H in dB versus F on a log scale. It has a gain of 20 dB in the pass band, as opposed to the passive RC low pass filter that we have seen, which had a gain of 0 dB in the pass band. And the corner frequency is given by the intersection of this low frequency asymptote and the high frequency asymptote, and that is 1.6 kilohertz. These two should intersect at a frequency which is 1.6 kilohertz. You can check that out. This is the first order filter, and we can see that from this function as well as from the plot here, this slope is minus 20 dB per decade. There is the circuit file available to you, so you can change, let's say, the C value or R1 value and predict what's going to happen, and then see if that indeed happens. Here is another op-amp filter, and this filter is also like an inverting amplifier with Z2 equal to R2 and Z1 equal to the series combination of R1 and C. So the transfer function VO by VS would be minus Z2 by Z1. Z2 is R2 and Z1 is R1 plus 1 over SC. And when we simplify that, we get this expression here. And this turns out to be a high pass filter with the corner frequency omega 0 equal to 1 over R1C, and F0 in hertz then is omega 0 by 2 pi, and that turns out to be about 1.6 kilohertz for the component values that we have in this example. And since we have already looked at Bode plots earlier, you can take this as an exercise. Plot the contribution of each of these terms, that is R2C S and 1 over 1 plus S R1C. You can obtain the Bode magnitude plot for each of these terms and then combine the three contributions to get the overall magnitude Bode plot for this filter circuit. And that should turn out to be a high pass filter function. Alright, let us now look at the plot of H versus omega, the magnitude of H versus omega, and that is what we have. This is the exact magnitude versus frequency plot, and if your Bode plot is correct, then you should get two asymptotes, one like that and the other like that, and those two asymptotes should meet at the corner frequency, that is 1.6 kilohertz. So this is 1 kilohertz, that is 2 kilohertz, and 1.6 kilohertz is somewhere between the two. Alright, so this is our pass band, and notice that there is a pass band gain of 20 dB for this circuit. Now, is this something that we could have estimated without doing this calculation? The answer is yes. What is this 20 dB? It is the gain in the high frequency region, and when frequencies are high, the impedance of this capacitance is very small, let's say 0, and then this circuit is nothing but an inverting amplifier, and the gain is minus 10k divided by 1k, that is 10 in magnitude, and that corresponds to 20 dB. Now in the low frequency region, what do we expect this slope to be? Let us look at this transfer function. At low frequencies, omega is small, so therefore this SR1C is small, and we can ignore that, and therefore our h of h is proportional to S. That means h of j omega is proportional to omega, and that gives us a slope of 20 dB per decade. So let us check if that is happening. Let us change the frequency from, let's say, 10 raised to 1 Hertz to 10 raised to 2 Hertz. That means we are going up in frequency by a decade, and as a result we are going from this mod of h to this mod of h, and that is 20 dB. So the slope is indeed 20 dB per decade. Here is the SIGWELL file. You can play with these parameters, the component values, figure out what this plot should look like, and then run the simulation and check whether your prediction is correct. Another circuit of the same type looks like an inverting amplifier. Our Z2 now is R2 in parallel with 1 over SC2, and Z1 is R1 in series with 1 over SC1. So the transfer function then is minus Z2 by Z1, and when we simplify it, we get this expression here. So now this circuit has got two poles, one at 1 over R1 C1 and the other at 1 over R2 C2. And it turns out that for the component values that we have here, this will function like a band pass filter with omega L equal to 1 over R1 C1 and omega H equal to 1 over R2 C2. If we substitute the numbers, FL turns out to be 20 Hertz and FH turns out to be 20 kilohertz. That is the plot. That is our pass band, and our FL is given by the intersection of this asymptote and that asymptote. So that should be something like 20 Hertz. This is 1 Hertz, 10 Hertz, 20 Hertz is here. So that is where these two asymptotes should intersect. What about the high cutoff frequency, FH? We look at the intersection of this asymptote with that one, and that should happen at 20 kilohertz. This is 10 kilohertz, this is 20 kilohertz. Again, the circuit file is available. Here is a filter circuit which has applications in graphic equalizer, and here is the reference from which it is taken. This book also has several other interesting circuits as well as many practical tips. So it's a good book to have in case you want to pursue electronics further. Alright, so how does it work? We have a pot here. The fraction of this total resistance on the left is A, and the fraction on the right is 1 minus A. So by changing this wiper, we are essentially changing this A here. When A is 0.5, VO by Vs is 1 in magnitude, and that gives us H equal to 0 dB. So that means there is neither any attenuation nor gain from the input to output. When A is smaller than 1, these two values here, then the output gets attenuated, and when A is larger than 1, these two values here, the output gets amplified. So by changing this wiper position, we can change the frequency response of this circuit very substantially, from this flat response to this band reject filter or towards band pass filter. So this circuit is used in graphic equalizer. Equalizers are implemented as arrays of narrow band filters, and this section is then just one of these filters. It has got adjustable gain or attenuation around a center frequency. In this case, the center frequency is somewhere here. So in a graphic equalizer, we will have several of these circuits with different central frequencies. Here is the SQL circuit file. You can change the value of A and see that this happens. This is a graphic equalizer, and this picture is taken from the internet, but we should clarify that it's not a commercial advertisement. Now these are those narrow band filters that we mentioned in the last slide. This one is centered around 30 Hertz. This one is centered around 60 Hertz, 120, 200, etc. all the way up to 12.8 kilohertz. So this covers more or less the frequencies that we can hear. And this slider here corresponds to the wiper that we saw in the last slide. And by changing this slider position, what we are doing is controlling the frequency response of that particular filter with a center frequency of 800 Hertz. And we can do that for each of these to obtain the frequency response, the overall frequency response that we desire. For example, we might want to suppress the low frequency components and enhance the high frequency components, etc. There is a class of filters called Sallen-Key filters, and here we will only take a look at one of those, a second order low pass filter. The circuit is given here and the component values are also given here, and the circuit is taken from this book by Franco again. How do we analyze this circuit? The op amp is working in the linear region, so therefore V plus and V minus are nearly equal. And what is V minus? That can be given by voltage division, because this current is 0. So V minus is RA by RA plus RB times VO. Let's call that VO by K. What about V plus? V plus can also be obtained by voltage division from V1, voltage division between these two components, because this current is 0, and that gives us this expression here. And finally we write KCL at this node. This current plus this current plus this current should add up to 0. Now combining all of these equations, we get the net transfer function H of S, which is given by this expression here. And you are definitely encouraged to derive it yourself, starting from these three equations here. Here is the frequency response. This is the pass band, and we can see that in this case there is some ripple here, and that is the high frequency section. What is the order of this filter? We already said that it is second order, but let us also check it with our magnitude plot. Let's change the frequency from there to there, and we see that the difference in H is about 40 dB from there to there. So this is a second order low pass filter. Here is the circuit file. Here is a more complex filter circuit, a sixth order Chebyshev low pass filter, and it is taken from Franco's book again. As we have seen earlier when we were talking about Butterworth and Chebyshev filters, Chebyshev filters exhibit this ripple in the passband, and we can see that ripple right here. And since this is a sixth order filter, there is a very sharp drop after the cutoff frequency, and this slope would be 6 times minus 20 or minus 120 dB per decade. Here is a third order Chebyshev high pass filter, and in this case we should be able to find the order from the magnitude plot. Let us see. Let's take this section going from there to there. So that is 60 dB, and this part is about 1 decade. So the slope is plus 60 dB per decade. That is what we would expect from a third order filter. A band pass filter taken from this book by Fiore. Here is a notch filter example, and that's the frequency response. What is the meaning of a notch filter? It's essentially a band reject filter, but the band is very narrow. So it passes most of these frequencies. The gain is 0 dB here, which means it is actually just 1, VO equal to VS. But at this frequency, which is a very narrow band here, the gain is extremely small, minus 40 dB or even lower. So what it means is that it will remove this particular frequency from the input while passing all others. And what is so magical about this particular frequency? Why would we want to do that? Let us see. This is 10 Hertz, this is 100 Hertz, this is 20, 30, 40, 50, 60. So this frequency, the center frequency, is 60 Hertz, and that corresponds to the power supply frequency in the US and maybe some other countries. So this circuit is removing a 60 Hertz component from the input signal. And why is that important? That is important because electronic circuits often pick up this power frequency noise or disturbance from the surrounding circuits such as SMPS and so on, which have a lot of switching activity, which happens at the frequency of 60 Hertz, and that corrupts our signals, and therefore that 60 Hertz component has to be removed. So that is where these notch filters are very useful. In summary, we have looked at several op-amp filters. It is a good idea for you to take one of these simple op-amp filters, hook it up in the lab, and check out its functionality. That is all for now. See you next time.